Everyone, and welcome to our presentation on digital forensics and incident response. I am Rahul Rama, and my partner is Sri Mahita Madira. Throughout this presentation, we will demonstrate practical tools and frameworks that are used in real-world cybersecurity investigations, showing you how theory translates into practice in the field of digital forensics. Before we dive into our project details, let's understand why this project work matters. Cyber attacks are becoming increasing sophisticated and frequently, with threat actors using advanced techniques that challenge traditional security measures. Organizations today face significant challenges in collecting, preserving, and analyzing digital evidence in the way that maintain legal administrability. Legal requirements demand prior chain of custody and evidence integrity throughout the entire process. Additionally, incident response must be coordinated with and time sensitive, as every minute of delay can result in the future damage or data loss. This is the problem space of our project addresses. We are addressing four key objectives that we believe are essential for understanding and implementing effective DFIR capabilities. Firstly, we will present standard forensics processes and methodologies that form the foundation of any digital investigation. Second, we will compare established incident response frameworks to understand different approaches to handle security incidents. Thirdly, we will demonstrate practical tools throughout live examples, showing you how these tools work in real scenarios. Finally, we will analyze integration challenges and propose solutions for deploying these tools effectively in organizational environments. Let's start with digital forensics processes. Digital forensic follows a systematic five-step process that ensure evidence is handled properly and can withstand legal scrutiny. The first step is collection, which ensures process evidence acquisition without contamination. And the second step will be preservation, which maintains chain of custody for legal admissibility. Every piece of evidence must be tracked in collection of presentation. Third step, examination, which involves systematic analysis of collected evidence using various tools and techniques. Fourth step will be analysis, where we identify patterns and correlate findings to build a comprehensive understanding of what occurred. Finally, the fifth step is reporting, where we document everything for both legal and technical audiences, ensuring our findings can be understood and acted upon. Now, we will see the incident response framework. We researched three major incident response frameworks to understand different approaches to handling security incidences. The first one is NIST, which provides federal government standards and guidelines that are widely adopted across various sectors. Secondly, SANS. It's an industry focused methodology which offers best practices that are practically popular in corporative environments. CERT emphasizes vulnerability management and coordination, focusing on the broader ecosystem of threat intelligence and information sharing. Each of these framework has its own strengths and is suitable for different organizational contexts. Let me now take you through each framework in detail to show you how they differ and when you might choose any one of over the others. The first one. Let's now discuss about NIST SP 861 framework. It provides a comprehensive four-phase approach that particularly well suited for government and large enterprise environments. The preparation phase establishes policies, procedures, and training programs that ensure organizations are ready to respond when the incidents occur. And this includes developing incident response plan, training teams, and establishing communication protocols. Next one will be the detection and analysis phase. In this phase, mainly focuses on incident identification and assessment using various monitoring tools and techniques to identify potential security incidents and determine their scope and impact. The containment phase. This phase addresses both immediate and long term response strategies, including short term contamination to stop the immediate threat and long term contamination to prevent recurrence. Finally, the post incident activity phase ensures lessons learned and continuous improvement. Documentations what happened, what worked, what could be improved for the future instance. This all will is the part of NST NIST framework. Now let's see the SANS incident response framework. Unlike the NIST, this is the six-step methodology which includes preparation, identification, containment, eradication, recovery, and lessons learned. Now let's see one step by step. The preparation phase. It focuses on building and tool deployment, ensuring that the right people and tools are in place before an incident occurs. And the second phase is identification phase. It involves incident detection and proper classification using various monitoring and detecting systems and identify and categorize security systems. And third is like the fourth phase is containment phase, where this ensures immediate threat isolation to prevent spread, which is crucial for minimizing damage and preventing further compromise. And the fifth step will be, oh sorry, fourth step will be eradication phase, where the root cause is removed. Then the recovery phase starts. Here, the system recovers and implements monitoring to ensure normal operation that can resume safely. And the last step is lessons learned phase. This is actually the addition to the NIFT one, where the drive this phase drives continuous process improvement and analysis what happened and how the response could be improved for the future incidents. Now, let's see the third framework, which is CERT coordination framework. CERT coordination framework emphasizes coordination and communication throughout the entire incident response process, making it particularly valuable for complex environments with multiple stakeholders. The preparation phase includes stakeholder identification and communication phase, which ensures that all the relevant parties know their roles and responsibilities. And the detection phase leverages coordinating, monitoring, and information sharing, allowing organizations to benefit from collective intelligence and early warning systems. The analysis phase involves collaborative investigation and intelligence sharing, bringing them together different perspectives and expertise to understand the incident more comprehensively. The containment phase requires coordinated response across affected systems, ensuring the containment actions do not conflict with each other. Now, the eradication and recovery phases benefits from the shared knowledge and resources, allowing organizations to learn from each other experience and pool resources for more accurate, effective response. Now, let's see the tools which we used in the real life scenarios. There are four tools which we used: autopsy, volatility, MISP, and the slew kit command forensics. We selected four complementary tools for our demonstration, which are like I explained now. So, the autopsy provides a comprehensive digital forensics platforms that a user-friendly interface for complex forensics analysis, whereas the volatility specializes in memory forensics analysis, allowing us to examine volatile, excuse me, a volatile memory for evidence that might not be available on the disk. MISP, and this enables threat intelligence sharing and collaboration, supporting the information sharing aspects of incident response. And the last one is Sleuth Kit, which offers powerful command line forensics capabilities for deep technical analysis. These tools work together to provide a complete picture of what happened during the security incidents. Uh, Yep. Let's explain each tool in details before we move to the demonstrations. The first step will be autopsy. The first tool will be autopsy tool. Yeah, this is an open source digital forensics platforms built on SleuthKit that provides a user-friendly GUI interface for complex forensics analysis. It works by analyzing disk images and providing investigators with powerful tools to examine digital evidences. The platform supports timeline analysis to understand activity chronologically, which is crucial for understanding the sequence of elements during an incident. Now let's just see what's the autopsy demonstration look like. Yeah, this is the autopsy tool demonstration, which basically contains uh, five steps included for the data. First step will be Selecting the host. In autopsy, a host represents a specific device or system being investigated. The first step is to select or create a host associated with the case. This allows you to logically organize data sources. And the second step will be selecting data source type. The autopsy supports multiple types of data sources. In this step, you should or you can specify the format of the evidence that you are adding. The common options might be like disk images, logical files, local disk, or even the memory dump, which is basically the RAM snapshots. And the third step will be selecting data source. Your, you should browse your file systems to select the actual file or folder that represents the data source file. This is actually the crucial step because the file you are uploading is the actual evidence file that will be processed, so accuracy here is very crucial. And the fourth step, which is configuring ingestion. The autopsy uses ingest modules to process and analyze data. In this step, you choose which modules to run, such as file identification types, hash lookups, and keyword searches. And final step is adding data source. Finally, you confirm your selections and autopsy begins ingesting the data sources. This step may take several minutes to hours depending on the image sizes and depending on the model selected. Process is shown. The progress is shown in the lower panel, and the results populate dynamically in the left side tree structure. That's it. Now the Mahita will be continuing with the other platforms.
Ability represents the gold standard in memory forensics. Disk analysis, unlike those, memory forensics captures the live state of a system. So that includes running processes, network connections, and even malware that exists only in the RAM. So what makes volatility powerful is its plugin based architecture. So we can run it on Windows, Linux, Mac OS. So it has process analysis to identify running malware, network connection extraction to trace communication, and registry analysis for system configuration changes, and malware detection for advanced persistent threats. We use this extensively for incident response when we need to understand what's happening in a compromised system at exact moment of capture. So uh, we have a volatility memory analysis demo. This demonstrates the real memory dump analysis on 635 MB Windows memory sample. You can see the comprehensive output showing dynamic forensic artifacts, suspicious process enumeration, and network addresses that reveal communication patterns, and file system artifacts recovered from volatile memory. So the hex dump on the right shows raw memory content being passed. Um, this type of analysis is essential for understanding advanced attacks that operate primarily in memory. Then we have MISP. This transforms threat intelligence from isolated data points to actionable intelligence. It's an open source platform, and it has these key capabilities, which include indicator sharing, where teams can collaborate to analyze threats. So it actually has a REST API architecture that enables integration with SIEM systems. So it allows automated threat detection based on shared intelligence. So it's particularly valuable for understanding attack campaigns that span uh, within multiple organizations or within multiple teams. Um, So this is Mist Threat Intelligence Platform demo. So this demonstrates real IOC extraction from our memory dump feeding into Mist's threat intelligence engine. So we can see multi-source threat intelligence correlation happening in real time. Uh, so the terminal output shows automated threat analysis workflow identifying 8 malicious indicators. Notice how the system provides threat indication and response recommendations automatically. That's what's powerful here is the automated correlation. MISP takes our forensic artifacts and then immediately checks them against the global threat intelligence databases. So that gives us context about already known malicious infrastructure and attack patterns. So that speeds up the investigation. That's what MISP is for. And then we have SleuthKit. It provides fundamental building blocks for digital forensics. It's like a low-level file system examination tools that work directly with raw disk images. We have already seen Autopsy doing this, but Autopsy provides a user-friendly interface, and this handles the TSK handles the heavy lifting underneath. So its key capabilities include file system analysis for recovering deleted files and timeline generation for establishing the sequence of events. And it also does hash analysis for file integrity verification. So it has like a CLI design, obviously, which is very perfect for scripting and automation. So we use Autopsy when we need GUI tools to examine what's happened, and we use TSK when we need to have the granular control over the forensic processes, or when we are building custom analysis workflows, which the already existing autopsy tool like GUI tools can't handle. So now we'll look at a case study where we simulate an end-to-end incident response. For that, we used online available data set that is DFRWS 2023 challenge. This challenge is called the troubled elevator. So the scenario includes a bank executive trapped in a malfunctioning elevator on June 29th, 2023. And the elevator is controlled by a Schneider M221 PLC controlled elevator system. So this scenario is perfect for demonstrating industrial control system forensics, which is a rapidly growing field as infrastructure like these are slowly becoming more digital. So the challenge required us to determine whether this was a mechanical failure or cyber attack or insider sabotage using real forensic data from the incident. So now we'll look at the demo. So uh, before going through the demo actually, let's look at how the code is structured. So this case study has the data set, which has a few components. So the first one is the documents folder. It has just a couple of documents showing us the programming manual for M221 PLC control logic, and the other one has just the network diagrams, the network topology diagrams of the target system. Then we have CCTV footage. Initially, we were provided with these Z01, Z02, Z03 files, and we have combined them and inflated it to get our CCTV footage. So the CCTV footage lasts over 1 hour and 17 minutes. And then we have the desktop memory dump. This is the memory dump from Wayne's office computer. And .raw is memory dump, and .zo1, .zo2. So these are compressed for large memory dump files. Then we have PLC memory dumps. So this is external RAM dumps and on-chip RAM dumps. There are two types of files. So starting with ext, that is external, and on-chip is on-chip RAM dumps. And here also the timestamps range from 2:35 to 4:05 p.m. And then we have network trace. Network trace just gives us the network traffic captured during the incident. So we also have written some scripts to analyze, which consists of four main parts. So the first one is parser and simulator. So this helps us analyze PLC memory dumps and simulate elevator control logic. Then we have MP4 bitrate viewer. So its purpose is to analyze the integrity of CCTV footage. So we get the CCTV footage, but we do write a Python script to generate bitrate analysis that gives us so that lets us know if there are any spikes or not to generate to know if the CCTV has been tampered with. And then we have URL extractor. This is to just extract URLs and web activities from desktop memory dump. Then we have Modbus Wireshark. Uh, this helps us analyze the network traffic. Okay, now we'll go through the demo. Uh, First, we'll start with network traffic analysis. So we'll capture the network traffic that has been captured during the incident. For that, you can use the tshark command, or you can look at it using the GUI, Wireshark GUI. So I've run a few commands here. So the first one tells me that there are 123,529 Modbus transactions, and all are using function code 90. Function code 90 apparently stands for read file record. So that's very unusual for elevator control. Then we we've run another command that shows us that the capture spans exactly across 2 hours, starting at 2:27 on June 29th and ending at 4:27 on June 29th. And I've run another command here that tells me that 10:45 and 10:130, these are the two commands that were monitoring the PLC continuously, but we were not able to find any attack commands in the network traffic. So we will move forward with PLC memory analysis. So the PLC memory analysis here shows us, first of all, it shows us the PLC configuration. So the IP address 192.168.10.45, we've already seen that here in the network traffic. So that can be uh, removed. So because it is the Schneider M221 PLC. Then we know that we know the elevator position, that it's currently at floor 1, but it was at floor 4. And there are limit switches, LS1, LS2, LS3, and all buttons are properly mapped. Then we have control logic. So a 10-second timer and 1000 milliseconds precession timer, both are configured. And then we have safety systems as well, which are door controls and limit switches for open and close detection. So this PLC memory analysis shows us that the elevator's internal state at 2:35 p.m. was like this. So the elevator moved from floor 4 to floor 1, matching the executive's journey pattern. So the thing is we have to go through all of the RAM files like this one by one, seeing or basically tracing the elevator movement from floor to floor, matching it with the executive's journey pattern from the CCTV footage, and we have to find any gaps. So all safety systems are properly configured. So this gives us a baseline before the incident. Then we can run the video analysis. For that, we will use a bitrate viewer.py. So this is our output when we run bitrate viewer. Bitrate variations happen across the video timeline, as you can see. There are a lot of spikes. Now, any unusual spikes and drops usually indicate tampering. So this helps us establish video integrity for our evidence. Clearly, this has been tampered with. So the idea here is to, as I said earlier, go through the PLC file, trace the elevator's movement from floor to floor, and trace it at this points in the video and see if it is matching or not. Following the processes that we've used in the demo itself, we have carried out the entire investigation, and this is our report. We have found the critical discovery that the video has been tampered with. So using the PLC data, we tracked the elevator's movements constantly throughout the incident, and then we cross-referenced it with the CCTV footage, and that revealed evidence tampering. So approximately at the 50th minute mark, there was a bitrate analysis image that showed a massive spike. This is followed by an 18-minute window with identical patterns to earlier footage, like from 13 to 19 minute, 6 to 8 minute, and so on. Then we have the digital evidence from Wayne's desktop. Autopsy analysis of her desktop revealed the smoking gun. Wayne had downloaded the original CCTV footage and she deleted the critical 18-minute window. And then she copy-pasted the earlier footage to cover her tracks during that entire time frame. And then she attempted to delete the evidence files from her desktop, but forensic recovery exposed her tampering. Then we have our conclusion, which is that Wayne herself has orchestrated this elevator malfunction because staging this accident could trigger insurance claims and give her a lot of money. And she used her access to manipulate the PLC programming, and she attempted to cover her tracks by tampering with the video evidence. Grounded us in industry-standard frameworks that guide real-world incident response. We've studied NIST cybersecurity framework, CERT guidelines, and SANS digital forensic methodologies. Understanding these frameworks was crucial because they provide the structured approach that makes forensic findings legally admissible. And we have also gained hands-on expertise with the complete forensic toolkit like Autopsy, Volatility, MISP, and T-Shark, and PLC Memory Parser, SleuthKit, BinWalk, and FFmpeg. And Our case analysis achievements demonstrate real-world forensic capabilities. We structured a multi-domain forensic investigation spanning network, memory, and video evidence sources, and we successfully correlated the evidence across these different domains to build a comprehensive timeline. Looking forward, we want to expand the dataset to include mobile, cloud, and network sources in forensic testing, and we want to automate the DFIR tasks through scripting that will speed up the evidence collection and reporting, making the forensic teams more efficient. And integrating compliance checks ensures forensic processes align with legal standards like GDPR and HIPAA. We should develop this training content based on our project outcomes to educate the next generation of forensic investigators. So finally, adopting DFIR tools like autopsy and volatility in academic and training settings will prepare the students for real-world forensic challenges who would like to get into these domains for jobs. And these are our references. Thank you.